Okay, so hi, this is Brenda Huppenthal. I am a graduate student with the Data Lab here at the University of Arizona. And this week we're going to be talking about autoencoders. So this was originally scheduled to be given last week, but we did switch that one out with the convolutional neural network examples. And the reason we did this is a lot of autoencoders are used in the image space, meaning that inside of their architecture, they actually utilize the convolutional layers that we discussed last time. So we'll see here that we will use them again on another simple MNIST example, and hopefully also why convolutional layers are helpful, as well as why autoencoders are useful. So while I would normally start out by talking about just the uses of an architecture before we get into the details, in this case, the reason that autoencoders are very interesting is just very highly related to the structure of the network. So we're going to start with the structure, and then I will talk about different use cases. So here we can see just a very, very high level view. In this case, these could be two-dimensional images. They could be one-dimensional input vectors, something of that nature. We have this sort of two-part architecture where this first half, known as the encoder, is going to take some sort of input and then slowly compress that down to a smaller size. And that small size representation of your input that is learned by the encoder is what we would call a code. You'll also hear the term latent space used for the basically the dimension that the code lives in, which we'll get into a little bit why it's called that. But after the encoder is capable of learning basically this reduced representation, then our decoder is meant to take that reduced representation and rebuild the output as close as it possibly can get to the input. So a couple of notes on that. Autoencoders are kind of unique in this space because they are a self-supervised learning algorithm. So normally, if you're talking about using like a fully connected neural network to do a task like classification, you would need to be providing for every single input a label that tells the neural network what function it's supposed to be learning. It takes this input, and now we're outputting this label. Or for a regression task, it would be taking some input and then assigning some scalar output to it. So that would be a supervised learning algorithm because we are providing the labels. Autoencoders, though, because we have this architecture that allows us to give it the input, and then we are trying to get something that looks exactly like the input back out of the decoder, what we can do is rather than giving it some sort of label, all we're doing is we are training the autoencoder to get the output looking as close as possible to the input. So we can do that basically by calculating a reconstruction error, or the error of how different your output is compared to the input. So the reconstructed output. So one example of how you might do that would be an L2 loss, which would be essentially pixel-wise, you're taking the square of the difference between your input image and the reconstructed output. There are different things you can do, though, like you can do cosine similarity. So on this really high dimensional 1D vectors, cosine similarity is essentially calculating the distance between which direction these are pointing in your like high dimensional space. So another note here, because the autoencoder has to try and learn some sort of identity function, but it's getting fed down into this really, really small size. So you can think that if you have this really big image and then you're just trying to get this, say, 28 by 28 image in our MNIST example down to just 16 numbers, so going from about 800 numbers to 16 numbers to describe your input, what the encoder has to do is essentially learn some sort of useful compression of that input. And to do that, it has to identify what are the most relevant features that need to be captured in order to reconstruct this image. And it also needs to learn which features can be discarded because they are not as important to our input. So we're just pushing all of this information down through a bottleneck, and the encoder must learn to preserve only the most important features to get through that small dimensionality bottleneck. Then some terminology that you will see if you're looking up autoencoders and things like that online is undercomplete and overcomplete. So an undercomplete autoencoder is typically what you would see. Undercomplete simply means that the dimensionality of this code is smaller than your input size dimensionality. which tracks with what we want to do with autoencoders, which is force it to learn some sort of reduced representation. On the other hand, we can also describe autoencoders as overcomplete, and that would be an autoencoder where the code size is actually larger than your input. So you're taking your input and either keeping it the same size or possibly expanding it larger. And because of the properties of neural networks, you can imagine that because you aren't trying to force it to learn some sort of reduced representation, the best thing that it could do is simply learn to exactly preserve the image going forward. So it's not really changing the image in any way. You would have these weights of 1, potentially, well, not the weights of 1, bias of 0, but every layer would just apply some sort of close to an identity function on your image. And it turns out that if you have these overcomplete autoencoders, you don't even, like, they would just learn some sort of linear function. They don't need nonlinear activation functions. You just want it to be passing it through exactly as is. So these are not very interesting to us in comparison to the undercomplete autoencoders. And let's see here. So in the type of autoencoders that we're going to be looking at, our code is some sort of discrete input. So the code is really some set of hidden neurons in the center. Maybe not hidden. You can expose those essentially and pass in your input and get that that code out. And if you were using it for some sort of compression task, you could then like save that and then later in time decompress that code back up to your original output if you're using this for some sort of data like storage. But it's discrete. So what that means is like if you have some sort of continuous input going in, it's not going to be able to completely capture that continuous space. It's going to have to set on only a couple. It will not be able to capture everything that you could possibly set in because it's a discrete space in the center. And circling back around to why we might also call this a latent dimension, with autoencoders and then with their cousin variational autoencoders, which are a probabilistic version of autoencoders. The idea is that if you have some sort of parameters that are controlling your input, maybe you don't know what they are, maybe they're just latent, meaning that we can never observe them. We want the autoencoder to try to learn what a representation of your input that is based on those latents. So maybe one example of a latent input would be we have our MNIST data set, but then we have inside of our MNIST, we have the different numbers, 1, 2, 3, etc. So you want to capture not only what the number structure is, so maybe you have just one line, one circle, and then the different ways you can arrange those would be creating different numbers. Another latent might be, okay, we have this structure, which is a 1, but then it can also be tilted. So we also want our code to be able to capture information like that. Tilts, maybe it's getting scaled up or scaled down, being translated the image. These are all latents which are from like this unobserved probability distribution generating the images, and the latent space should be able to capture that. And if you have these continuous latent variables, then obviously a discrete space for the latents is not going to be able to perfectly capture that sort of information. Okay, so that was a very high-level overview of what autoencoders can do. I'm certainly willing to answer any questions if you have any in chat. But without it, we can go ahead and move on to talking about some properties. We have talked about some properties, like the fact that the latent space can only take discrete values, but other properties would be that when you train autoencoders, because you're not giving any labels, you're just telling it, I need you to find some sort of reduced representation of this specific image such that I can reconstruct it later. They're very data specific. So they're only going to be able to work well on data that you feed it that is very similar to what it saw in the training set. It learns some sort of good reduced representation for that training data, but that's not necessarily something that translates well across different tasks. As a very extreme example, you can imagine training an autoencoder on the MNIST data set. So it's learning about these lines, these circles, potentially how they're arranged, angles and things like that. And then if you give it a picture of a cat, none of those features are going to be very relevant for the new input that you've given it. So the representation it's going to derive for that is going to be very very poor. It won't have learned any features that are good for identifying cats. It only knows features that are good for identifying digits. So you wouldn't expect the autoencoder to perform well on that new task. And generally, autoencoders don't perform well outside of the underlying support of what they were trained on. Second note is that autoencoders, the codes that they produce are a form of lossy compression. So in compression, there's two basic types, which would be lossless and lossy. Lossless means we have some sort of compressed size, but we can perfectly reconstruct the input. Generally, you can't push it down as far because you can make no approximations. It's very restricted because you must be able to perfectly reproduce it. Whereas with autoencoders, because we're feeding it through this very small bottleneck, this very small code, it will necessarily lose some features during that process. And you want to design it so that you're not losing important features, but you can disregard unimportant ones. So you might lose like noise in the image or things like that that the autoencoder did not learn to capture well. And then as we discussed, autoencoders are also self-supervised because all you need to do is give them the training images and then tell it basically, here's how you would construct the reconstruction loss, L2 or cosine similarity or something else in that area. And it will be able to learn useful features without any further input from you. So autoencoders, because of this, have a lot of use in images and also for compression and for feature extraction. So talking about some of the image applications first, we can tweak the inputs and then have the autoencoder try to learn not an identity function, but a function that's going to do something else of interest. So like denoising. In this example, we would have our input images and we would artificially noise these. So you can add, say, a Gaussian noise to every single pixel, or you could add like salt and pepper noise, which is like just black pixels randomly, white pixels randomly. But then you will train the autoencoder to reconstruct the original image that has not been denoised. So then the idea is that the autoencoder learns some sort of function that to the code captures important information while disregarding the noisy signal. And the decoder can then take that code and reconstruct an image that has no noise in it. Image reconstruction and colorization are both very similar ideas. Reconstruction, or you'll also hear about like image infill. That would be some area of the image. Maybe you just put a box over it and it's a box of black pixels. And what you want the autoencoder to do is learn to figure out, to create some sort of input for those pixels as well. So you would just mask some part of the image with black pixels and then test the reconstruction loss against what was actually inside of those pixels to force the autoencoder to learn some sort of completing function for those areas. And colorization, again, very similar, except that we would then just grayscale the images as the input and then compare the reconstructed colorized image against our original color image. Because autoencoders learn this reduced code size, what you can do is use them for dimensionality reduction. I believe we spoke about that earlier in this class, various methods of doing dimensionality reduction, such as principal component analysis. But this would be a way of taking the codes that it creates, possibly you can force it down into 2 dimensions and then plot those to see if there are any interesting maybe clusters that you can draw inside of that or features that you notice in your data in this reduced dimension that has been learned by the autoencoder. We've spoken about compression, just that this smaller size is easier to store and then can still be inflated back up to the original size for whatever your input is. And more generally, and what a lot of autoencoders end up being used for is feature extraction. So because they are learning some sort of useful representation for your input without any additional like labeling work needed on your side, you can essentially just let the autoencoder run. It will learn these useful features and this useful code representation of your image. And then what you can do is essentially just break the autoencoder into 2 pieces, take your encoder, and now that's just a feature extractor. So it has learned a useful representation. It has kept features which are important and disregarded ones that are not. And you can use that as a first step in any other type of learning task that you would like to do. So if you wanted to do classification, but you have a ton of images, and it would be very hard to run a classification network on these high dimensional images because you don't have, for whatever reason, the capacity to label all of them, or enough of them to train a classifier totally. You can use this autoencoder to get an encoder that's extracting useful features and then put a smaller network on the end of it. And all that network is doing is learning the classifications for some smaller set of images. The idea being that if you've learned a useful representation, it should be easier at that point to take that representation and classify it. And you would need less labeled data to do so. So you could use any sort of network on the end of that. So then rather than having that network learn all of the features, you have, in a self-supervised manner, learned the features using the autoencoder. Okay, so that is the end of just a very high-level view of what autoencoders are and what we can use them for. I have put together a notebook that has 2 examples of autoencoder architectures, and I will share the link to the notebook in the chat. Okay. Give everybody a second to make sure that we are on the same page here. Before, I would not recommend running this notebook right now. It has all of the outputs that I've already generated, and the first autoencoder in particular takes about 20 minutes to train. So we'll just scroll through it, take a look at everything, and talk about the code. But I did try to set this up so that if you want to make changes to the architectures and then train them and see how they operate, it should be very easy to do so. So this notebook also was trained using a GPU because we're starting to get into larger sizes of networks, which means that it will take just longer on the CPU than it would on the GPU. To that end, I have shared a tutorial here that's going to show you how to connect to a runtime with the GPU on Google Colab, but I'll also show you very quickly here. So you'd come up here and click on this drop-down menu, and then you can change the runtime type. So if we were to come in here, you can see that there are a couple different variables you can change. Here you can see that Google Colab will also let you run R in a notebook. And then here it will let you choose between different hardware accelerators. So I believe if you're just opening this and you've never used a GPU before, it should have you set on CPU, but then you can select from any of these other ones. The free version may not let you do that. And another part of Google Colab is that while they will provide you some use of their GPUs for free, it is dependent on what the load on the on all of the GPUs is at the time. So it may not always be available depending on how many users on the paid tier are attempting to use it. And it does want you to be actively on this notebook, so you can't let it train and then walk away. It will disconnect your runtime to provide the GPU to someone else. So it wants to see activity from you in here as well. Okay. So in this notebook, what we're going to do is look at 2 autoencoders. One of them is going to have just fully connected layers. And we will look at training on MNIST using a mean squared error between our image and the reconstruction. I'm also trying to expose you to some of PyTorch and PyTorch Lightning, some of the features and functionality that those libraries provide to you. So that will be, we'll talk about that in the first example. And then in the second example, we're going to level up that architecture by using convolutional layers because we are working with images. And we'll talk a little bit about, okay, using the convolutional layers in the encoder means that to get down from our code size back up to a larger size, we'll have to use these deconvolutional layers. So the first thing is installing Lightning, which is kind of a wrapper on PyTorch. We'll see why it's interesting in a second. And importing various libraries that we will need. The first thing to note here is that we are just using the MNIST dataset from MNIST, the MNIST dataset that is stored on TorchVision in the TorchVision library. So if you click through on that link, you'll see that they actually have many different types of data sets that you can use. These are specifically computer vision oriented. So you'll see things like MNIST, Celeb A, which is a celebrity face data set, and other image-based data sets like that you can use to just play around with different models. Notably, it's going to download these in PIL format, which is Python Imaging Library, another library that you can import, and that will make it very easy to make these visualizations. Okay, so with pretty much any neural network, when you're doing training, we're going to go through just the main steps of that, which would be loading the data set, defining our architecture, training, and then testing. So first, loading the data set. Just 1 second here. Okay. So we're going to be using torchvision.transforms to help us with this. The first thing to note is because we have our input images, the MNIST images in this PIL format, we actually need to change them to get them as tensors in a format that our neural network is going to be able to consume. And TorchVision provides us with some tools called transforms, which we will use to apply sequentially to our data in order to change from the PIL to the format that we need for the neural network. So the transforms that we are applying specifically would be, the first one is we turn it into a PyTorch tensor, and then we are going to normalize it. Normalizing data just generally helps in the machine learning sense. And in this case, what we're going to do is set the mean of every pixel to 0.5 and specify the variance as well. So a mean shift and then along a normal distribution. The last thing we will do here, because we are using a fully connected neural network, it expects our data to be in a vector form. So rather than feeding it this 28 by 28 image, we need to turn this into a 700 some odd array or list. That's just one dimension because then we will feed it through these fully connected neural networks layers. So transforms just gives us this feature called compose, which means that we get to list the number of transforms and the order that we want them to happen in. And then when you give that to the data loader here, it's just going to automatically apply that to every single PIL image that it loads. So after we load, it's already going, all of these steps will be applied and it will be completely ready for our model. So in these steps, we're just loading the data set. And then here we need a data loader, and all the data loader does is wraps our data set in some sort of iterable. So our data set is just one-off images. The data loader is going to package those up into batches for us. And then every time you call it, it's just going to give you one entire batch. So very helpful. We're just going to pass everything into Lightning, and then Lightning can call on that and get the next set of data that it requires. Okay. Next up, the architecture. So here, let's see, all we're doing is using these linear layers, and that's just a fully connected layer. Very simple parameters here. The first argument is going to be the input size that it's expecting coming into the network. And then the second is going to be the output size coming out of that layer. So you can see in this decoder, we are stepping down from the total input size to 512, then down to 256, 128, and finally down to our latent dimension size. And I went ahead and set this up so that if you would like, you can change the input size and the latent dimension by calling it with a different size here. So it should be very easy to just play around with different latent sizes. The decoder goes in the exact opposite direction. You can define more complicated architectures on either side of this, probably more helpful for the decoder. But in this case, we're just going to make it completely symmetric. And then the encoder and the decoder also have these forward methods. And all forward means is every time you pass in an image, it defines how it takes this forward step or how it takes your input and calculates the output. So in this case, we just encapsulate everything as all of these layers. So we just pass it through every single layer in the network. Okay. Then our autoencoder, it's going to create an encoder and a decoder by calling those classes and instantiating them with the input size and the latent dimension size. So here I just have defaults that will work for the MNIST dataset. It's only slightly more complicated here. So in this case, the forward step, it needs to pass it first through the encoder, and then we're using this Z variable to store the code. And then it passes that through the decoder to get our reconstructed size. The loss, we're using this RMSE loss. And then for every training, validation, and test step, we need to calculate the loss based on the results of the batch. And then simply here for training, I define this optimizer. So we're going to be using Atom, and it's using a learning rate of 0.001. Okay. So for training, this is really where Lightning comes in. So you can see that we have created this autoencoder using a Lightning module. And the Lightning module basically just makes it so that after we define the training steps and the test step, it is going to basically be able to fit that for us. With PyTorch, we would need to define some sort of loop that handles the logic of getting the next set of data, passing it through training, updating all of the gradients, and doing the stochastic gradient descent. But with Lightning, we can simply tell it, here is what our trainer is going to be. So we tell it that we have a GPU and that we would like to use it. And also, this early stop and callback just means that if your validation loss stops updating after 3 epochs, we can just go ahead and call it quits before we start to overfit to our training data. So after telling it, here's what you can use to train, and we want you to stop at this point, all we have to do is call this trainer.fit model, or fit method, excuse me, by passing it the autoencoder and then the data sets that it's going to load from. Okay. Now with that done, let's see, we can come down here into the visualization step. So we're simply comparing images. This is going to compare between the input image and then the reconstructed image that the network has given us. So here, we're just going through the first 5 images. The reconstruction, we pass our image through the autoencoder and compare them. And you can see that this has managed to, this is what the decoder has learned to reconstruct. So it's pretty patchy. It has started to learn some of the features of the input, but it's clearly not as good as we would hope. So this is not very surprising. It shouldn't be, because we've talked about how fully connected networks are not very good at capturing structural information, and that convolutional neural networks are better. So we are going to now try to take our autoencoder, put some convolutional layers in it, give it a little bit more representational power, and then see what kind of outputs we can get. Okay. So again, starting from scratch, but we'll be able to go through this much more quickly this time by only talking about the differences that we're making. We're going to load the data set again, but in this case, because the convolutional layers can take the 28 by 28 images, you can see that while we still convert them to tensors and we normalize them, we no longer need to do this flattening step. So we now normalize our images, but they are still square. In the encoder and the decoder, we can see that the fully connected layers have been replaced by these 3 layers here. So the first one is just a convolutional layer, passing the kernels over the input, where we're trying to learn kernels that give us some sort of useful function that finds some feature of interest in the underlying image. So we're going to pass it through 3 of these. The specific input and output size are determined essentially by the kernel size, the padding, how far the kernel is striding, and things like that. The math is not that interesting. If you would like to see the math, you can come to this convolutional 2D. Let's just take a quick look. And you can see here that it's giving you, okay, for some sort of input size, the output size is a function of the input height, our padding, the kernel size, and the stride. Which, if you actually want to design these from scratch, it's important to be able to calculate that in order to make sure the size of all of the layers connects well, but it's not really that interesting. But after going through that math, we can see that in this case, the latent size that I'm going down to by passing for 64, 32, then 16 filters through, we've made it down to an image, quote unquote image, reduced image, that is 16 by 3 by 3. So from about 700 input size, we've gotten down to about 150 as our latent dimension. And then in this case, our decoder uses essentially the reverse of that operation. So with our convolutional layer, every time we pass a filter over it, we reduce the size. So what the deconvolutional layer needs to do is essentially a convolutional operation that has an additional step of taking a single pixel and then upsampling that into a patch of pixels in this larger output image, which is not that complicated. It'll just take exactly that value and say you want to project one pixel up into 3 by 3 to make your image 3 times larger. It just would copy that into all 9 pixels in that little square. And then everything inside of our CNN autoencoder is actually the exact same. So here we simply use the new modules that we just defined that use the convolutional neural network layers. But then everything else in here is kept the same. For training, the only thing that I've done here, just to show you that this can be useful, is I've added one more callback called model summary. So the model summary just means that when we start training, before the trainer starts, it's going to print out a list of every layer that we have inside of our architecture, as well as the number of parameters. So just taking a look here, I'm not sure why it printed out twice, but we can see that our encoder, at the lowest level, these are all of the parameters. And then at the very high level for this entire module, it has 2,000 or 23,000 parameters in the encoder and 13.2 parameters in the decoder. And that you can see here as well, it captures all of the trainable parameters for our CNN architecture, which should be significantly smaller than the fully connected network. This one, I believe last time I ran it managed to train in just a couple minutes after 20 epochs. We can see that this is giving us significantly better results. The images are less patchy. Interestingly, you can see that, well, for example, the input has a bit of noise just at the end of this 5 where it's dropping a pixel. This has managed to capture some idea of a 5 where that is just a straight line across and this noise has been discarded. You can also see that the RMSE errors that we're getting are significantly lower. In this case, we're getting an RMSE of 23, whereas in the fully connected layers, we can see that our RMSE is basically an order of magnitude above that. So one more thing to note here, I'm cheating a little bit because the fully connected network is basically forcing this down to, let me see what the size was at the very center. My apologies for scrolling around. So we can see that the fully connected network is going down to 64 bits only. So it's kind of hobbled by the fact that it has a slightly smaller 64-bit representation that needs to get down to, whereas the CNN can go down to 144. So the CNN is basically enjoying having a slightly larger latent dimension size, as well as being able to use the convolutional layers, which work better with images. Okay. You see that's really bad at this particular 4 as well, but the rest of the images seem okay. Okay. So I've also prepared a bit of a take-home example if anybody is particularly interested in continuing with this. We talked about the fact that autoencoders can be used in denoising applications. So I have put together a bit of an example that you can then take the architectures that we've just played with, apply them to this example, and then see what the outputs are. So in this case, I set this up in the assumption that you can use the convolutional neural network architecture, so we do not have that flatten step here. If you're going to use the fully connected one, you'll need to add that back in here as well to turn it into a vector rather than this 2-dimensional image. And here I have some useful functions. What these are going to do are add 2 different types of noise to our image. So the first one is Gaussian noise. Very simple to do with NumPy. We are simply taking a random number, and Torch's rand n will draw from a normal distribution with a mean of 0 and a standard deviation of 1. So we're simply taking that and then multiplying it by square root of 0.1 in order to change the variance. So we're not changing the image by too much. But you can certainly play with that parameter as well to see how much adding way too much noise would negatively impact the autoencoder. We simply just add this noise to our initial image. And in this case, I've decided to show just a grid of one example where this is the image which has the added Gaussian noise. So you can see that even this is pretty high, that these pixels are getting washed out to black, so it sees this discontinuous feature here. And then the second example for noise would be salt and pepper noise. Both of these are pretty widely used when you're looking at like denoising examples and proving a network's capabilities in performing denoising. But so for the second one, salt and pepper, the output of the salt and pepper is going to be, it's going to randomly flip some pixels completely white and randomly flip some other pixels completely black. So you can see in this case that we have all of these, the completely white pixels are easier to spot than the completely black ones. And partly I believe that is because you have completely black pixels hitting in here, so it's not changing the actual output, what the image looks like at all. But you can see that in this case down in here, there are some images that also got flipped to be black instead of white. So in this case, rather than make a function that does that completely from scratch, I am using the random noise function from the scikit image library. That is one of the ones that we imported at the top. So we're simply telling it, okay, please make some new salt and pepper noise on top of this image, and then we will return that image back into Torch tensor. So we need to do this particular one because the random noise requires a NumPy vector input, and then Torch, obviously, PyTorch will require the Torch tensor again. So this is convert this back into a NumPy array, and then convert this back into a tensor. Okay. So the example here would be pretty simple. You can just define an autoencoder architecture. So as a hint, just try and reuse one of the architectures that we have so far first before you start playing with it. You can just copy and paste the collab cell down here, train it, and then one note when you are training is this input image. We did not apply these noises as a transformation for the input because we still need the original image output. So when you're giving that, like while it's training, you need to run the forward step on the noisy image rather than the unnoised image. But then you're computing the reconstruction loss with the image without noise added. And then you can visualize the results in the same way that we've been talking about. So that's something that you could work on now while we're here. Would be certainly happy to help you out with it. I would also be very happy to answer any more questions about autoencoders that you might have at this time. Okay. Well, a nice short one today. Thank you very much for stopping by, and please join us again next week. We are going to be discussing GANs, or generative adversarial networks, which is particularly interesting and uses some of the same ideas in terms of learning a latent space, but now instead of doing tasks like classification or regression or things like that, we actually want to be able to train on a data set and then create new images that resemble the underlying data set. So very interesting topic, and I hope that you can come through. But besides that, thank you, and I'll go ahead and stop sharing.